In the heart of Rome, a vast, unseeing eye has stared into the heavens for nearly 1,900 years. This is the oculus of the Pantheon, the center of what is still the largest unreinforced concrete dome on planet Earth. Across the water in southern France, the three-tiered stone arches of the Pont du Gard have spanned a river for 2 full millennia. How did a civilization without modern computers or power tools build structures that have outlived the empires that followed them, while our own concrete can crumble in a few decades? Welcome to 10-Minute History. I'm your host, Jake Sullivan, and today we're uncovering the hidden science behind the concrete and conquest of the Roman Empire, to learn how engineering, not just armies, built the ancient world's greatest superpower. The Roman Empire at its peak was staggering, ruling over 5 million square kilometers and 70 million people, nearly a quarter of the entire world's population at the time. While the famous legions conquered this vast territory with the sword, it was the engineer's trowel, level, and plumb line that held it all together. Roman engineering was a fundamental tool of the state, a physical manifestation of the asterisk Pax Romana, the Roman peace. It was the skeleton upon which the flesh of the empire was hung, a system so robust that its bones still protrude from the landscape of the modern world. And at the very heart of this revolution was a single, miraculous material, Roman concrete. The Romans called it caementicium. While they didn't invent the idea of mixing a binder with filler, they perfected it, transforming simple mortar into a structural material that reshaped the world. Roman concrete had 2 main parts, the aggregate, which was the filler, and the mortar, which was the glue. The Romans were incredibly clever about their aggregate. For foundations that had to bear immense weight, they used heavy, dense stones like basalt. But for the upper parts of buildings, like domes, they used lighter materials to reduce stress. For the very top of the Pantheon's dome, they used lightweight pumice, a volcanic rock so porous it can actually float on water. This graded use of material, from heavy at the bottom to light at the top, was a masterful stroke of engineering. But the real secret, the magic ingredient, was in the mortar. It started with lime, which they made by cooking limestone in kilns. But then they added a special volcanic ash called pozzolana, named after the town of Puteoli, near the Bay of Naples, where the best deposits were found. When this pozzolana ash was mixed with the lime and water, a powerful chemical reaction occurred. It formed a new, incredibly stable crystalline structure, a compound we now call calcium aluminum silicate hydrate. This new compound was the key. Unlike regular mortar that hardens as it air dries, this mixture hardened through a chemical process. This meant it was hydraulic. It could set and harden completely underwater, something that was impossible before. It also meant it was exceptionally strong and durable, forming a powerful bond with the aggregate to create a single, monolithic structure, more like a synthetic rock than a man-made building material. Nowhere is the genius of Roman concrete more breathtakingly displayed than in the Pantheon. Its dome is a perfect half-sphere, over 43 meters, or 142 feet, wide. For more than 1,300 years, it was the largest dome in the world, and it was built without a single piece of steel reinforcement. Its survival comes down to meticulous design. As we mentioned, the concrete at the base of the dome uses heavy aggregate, which gets progressively lighter as it rises, ending with feather-light pumice at the top. The dome's walls are also over 6 meters thick at the base, but taper to just over 1 meter thick around the central oculus. The beautiful sunken panels on the inside, called coffers, aren't just for decoration. They remove tons of weight from the dome without weakening its structure. The Pantheon is a building that simply could not have existed without Roman concrete. It is a perfect symphony of material science and architectural vision. But if the Pantheon shows concrete's elegance, the Colosseum shows its brute strength and efficiency. That massive amphitheater, capable of holding up to 80,000 people, was built in under a decade. This was only possible because of concrete. Instead of needing thousands of skilled stone masons, the Romans could use largely unskilled labor to mix the mortar, carry the rubble, and tamp it all down into wooden molds. This democratization of labor allowed the Romans to build on an industrial scale, a feat as impressive as the monuments themselves. With this wonder material in hand, the Romans set out to solve one of the biggest problems facing any major city: water. By the 1st century AD, Rome was a sprawling metropolis of nearly 1 million people. The local Tiber River was polluted, and wells were not enough. Roman culture was a water-centric culture, defined by the huge public baths, or cantormai, which were social hubs for everyone, rich and poor. To feed this insatiable thirst, Roman engineers built 11 major aqueducts, a network stretching a combined 420 kilometers. The genius of the system was its elegant simplicity. It was almost entirely gravity-fed. This required finding a pure water source in the hills, at a higher elevation than the city, and then engineering a channel with a continuous, gentle downward slope for miles on end. The precision required was staggering. The optimal gradient was incredibly slight, sometimes a drop of just 1 meter for every 5 kilometers of distance. To achieve this, Roman surveyors used an instrument called the asterisk chorobites. It was basically a 6-meter-long wooden plank with legs and plumb lines, and a groove on top. For precise measurements, they would fill the groove with water. When the water was perfectly level, they knew their instrument was level, and they could take sightings to maintain their gentle slope across the land. Now, contrary to the popular image of grand bridges, about 80% of a Roman aqueduct's length was actually underground. These were rectangular channels, or asterisks spicus asterisk, dug through the earth and rock. Building underground protected the water from contamination, kept it cool, and was much cheaper than building bridges. The inside of the channel was lined with a special waterproof concrete called opus signinum asterisk, which used crushed terracotta tiles as an aggregate, making it exceptionally watertight. So what about those iconic multi-tiered arches we all think of? Those were the expensive, labor-intensive solution used only when necessary to cross a deep valley or a wide plain, all while maintaining that perfect, gentle gradient. The Pont du Gard in France is the most spectacular surviving example. It's nearly 50 meters high and was part of a 50-kilometer system built to supply the city of Nimes. The gradient of that entire 50-kilometer aqueduct was only 17 meters, a testament to the surveyor's incredible skill. Once the water reached Rome, it was managed by a high-ranking official called the asterisk curator aquarum asterisk, or water commissioner. One of the most famous, a man named Sextus Julius Frontinus, wrote a detailed report in the late 1st century AD. He complained bitterly about citizens making illegal taps into the main water lines to steal water for their private homes. He also described the clever distribution system that prioritized public needs. The pipes leaving the main distribution tank were set at different heights. The lowest pipes, the last to run dry in a drought, supplied the free public fountains. The middle pipes supplied the public baths. And the highest pipes, the first to fail if water levels dropped, supplied the wealthy private customers who paid a water tax. The aqueducts were the circulatory system of the Roman city, delivering not just water, but civilization itself. If the aqueducts were the arteries of the empire, the roads were its sinews. The saying, quote, "all roads lead to Rome," is a literal truth. The asterisk, Viae Romanae asterisk, or Roman roads, formed a network of over 400,000 kilometers, 50,000 miles of which were paved. Their primary purpose was military. A paved, reliable road allowed a legion to march up to 25 miles a day, a strategic force multiplier that allowed a smaller number of soldiers to control a huge territory. Road building was part of the process of conquest. After an area was pacified, the army would immediately build a road through it, a permanent line of Roman power carved into the landscape. Roman roads are famous for two things: their straightness and their durability. Engineers used a tool called a asterisk groma to lay out straight lines, and they were not intimidated by terrain. If a hill was in the way, they would cut through it. If a marsh was in the way, they would build a stone causeway across it. This relentless straightness was a symbol of Roman determination. Their legendary durability came from a standardized, layered construction method. First, they dug a deep trench down to firm subsoil. The bottom layer was made of large, packed stones. Above that was a layer of smaller stones and gravel, often mixed with concrete. Then came a layer of sand and cement. Finally, the top surface was made of large, perfectly fitted paving stones of a hard rock, like basalt. Crucially, the road surface was cambered, meaning it was higher in the middle and sloped down to the sides. This allowed rainwater to run off into drainage ditches, preventing water from getting into the foundation and causing damage. This masterful drainage is one of the main secrets to their 2,000-year survival. Along these roads, milestones, or miliaria were placed at every Roman mile. They marked the distance, but more importantly, they were inscribed with the name of the emperor who built or repaired that section of road, turning every mile marker into a piece of imperial propaganda. This network enabled the cursus publicus, the state-run postal service. A system of relay stations with fresh horses allowed official government messengers to travel up to 200 miles in 24 hours, a speed that was vital for governing a vast empire. So what does it all mean? The concrete, the aqueducts, and the roads were the essential operating system of the Roman Empire. They were the tools that transformed conquered lands into integrated provinces, fostering a unified economy and a shared culture. The collapse of the Western Roman Empire in the 5th century was also a story of infrastructure decay. Without a central government to maintain them, the roads crumbled and the aqueducts failed. Cities, starved of their water supply, shrank dramatically. Critically, the recipe for hydraulic concrete was lost for over 1,000 years. The inability to maintain the systems that supported a large urbanized society contributed directly to the fragmentation of the early Middle Ages. And the legacy continues today. Scientists are now studying the chemistry of Roman seawater concrete, which they've discovered is a self-healing material that gets stronger over time, hoping to develop a more sustainable green concrete for the modern world. And many of Europe's major highways still follow the straight lines first surveyed by Roman military engineers. The Romans understood that infrastructure is destiny. They knew that to build an empire that would last, you first have to build the systems that sustain it. They built for eternity, and in the enduring shadows of their aqueducts and the unerring lines of their roads, they came closer than any civilization has before or since. So, what are your thoughts on this? What piece of Roman engineering impresses you the most? Let us know down in the comments below. If you found this interesting or learned something new, please give this video a like, and don't forget to subscribe to 10-Minute History for more deep dives. Thanks for listening.